And you can think about that as kind of a convexity in the cost structure, right? That is, you have a rising marginal cost. So rising marginal cost, of course, corresponds to convexity in the overall cost, right? And you could restate that problem. We did it as an equilibrium problem. You could restate it as a maximization problem. And for a lot of purposes, it can be useful to take what would be a competitive equilibrium problem and translate it into a maximization problem. And the simplest way to think about doing that is if you had a demand function, d of x, right? So you have some demand curve. Here's x, here's the price of x, here's d of x. Then you can think about, so this is an inverse demand function, right? Because if it's a function of the quantity, this gives you the height of the demand curve at a given point for a given quantity x. Think of that as like a marginal value schedule. Then you can say define v of x equals the integral from 0 to x of d of z dz. Okay, it's sort of the integral. It's the area under the demand curve. Then dv dx, of course, by the fundamental theorem of calculus, would be equal to d of x. That is, the derivative of this function v would be equal to the demand function I'm interested in. Similarly, on the cost side, if you had a supply function with the height of the supply curve, here's some argument x, call this supply function s of x. So again, it's the height of the supply function. It's an inverse supply function, actually. It's telling us the height of the curve at any given point x. Then what we could say is we could define c of x equals the integral from 0 to x of s of z dz. And of course, for that same reason, dc of x dx would be s of x, right? So in other words, if I had a supply function, I could think about it as corresponding to some corresponding cost structure. And if I had a demand structure, I could think of it as corresponding to some total value schedule. And so then if I wanted to think about a competitive equilibrium, I could think of maximizing what you might think of as a total surplus, maximize from 0 to infinity e to the minus rt, v of k, if that's the capital stock at day t. So that's the value created by the capital stock at day t, minus, call it k of t, minus c of I of t, where that's the amount that I invest at day t, dt. So I could restate my equilibrium problem as corresponding to this maximization problem. Right? So that would be my maximization problem. I'm maximizing what some people call this maximizing total surplus. This is the present value of the surplus created, where this is the value of the capital stock I have minus the cost of investment every period. So this is the surplus generated in period t. Okay? People understand how that works? And because I defined the value from the demand curve and I defined the cost from the supply curve, the derivatives of these things are going to give me my usual first order conditions. The first order conditions to this problem, I should say, are going to correspond to the equilibrium conditions of the underlying competitive equilibrium, right? This is a trick that we often use to restate a competitive equilibrium problem as a solution to a surplus maximization problem. Okay, and the reason it's nice to be able to do that is there's lots of algorithms out there, a lot of theorems we know about maximization problems that will then carry over to help us find the solution to this competitive equilibrium problem. Everybody understands that? So we started maybe thinking of it as a competitive equilibrium problem and say, well, that competitive equilibrium problem is really isomorphic. It's really identical to the corresponding maximization problem, the surplus maximization problem that looks like this. Okay? Yeah, so well, no, not quite. This won't correspond to the true surplus, right? In other words, what you might be saying is this V function I'm using isn't really the social value. But as long as it's the integral of the demand curve, it will generate the competitive equilibrium. It won't be maximizing the true social surplus, right? The true social surplus won't be given by this formula because this V won't be the true surplus function. But this V will give me the competitive equilibrium because the derivative of this thing is, you get the idea? I've integrated, I've just said, whatever the demand curve is, maybe there's externalities, maybe there's anything. I'm just going to integrate the demand curve, call that V, so that the derivative of that, the first order conditions of this are going to correspond to that equilibrium problem. All right, so there's a lot of time. Now, it's not always going to be true that every competitive equilibrium can be expressed as a maximization problem. There are going to be problems that can't. This particular one, like say K had some externality, that every time we produce K, it produces pollution, or I produce pollution. This would still give me the equilibrium, right? Because this is the first, what's the first order condition for this problem going to be? Well, we have to figure out how we're going to maximize this, right?